So today we will be covering, yes. So today is the lecture 4, and before I start today's session, actually I have a very tight schedule today, so we will try to wrap up by 4:52 or 53, and the remaining 6 to 7 minutes I will be discussing the whatever doubts you have, because sharp at 5 I have to disconnect today. So that is something that I want to share before I start today's session. So yes, so what we covered yesterday is a little bit about the quantum, like qubit and that thing. So, qubit versus quantum system and its representations. We have seen that part. A little bit of the observables and also the linear algebra extensions. Let me just mark it in this way, extensions. So we covered this part, whichever is required for quantum mechanics, where primarily we have looked into the Hermitian or the self-adjoint operators and its implications in quantum theory. And also what we covered is a little bit of, I guess, the interference. We talked about that. And the interference and the relation with the probability amplitudes or probabilistic amplitudes versus the probabilities. Okay, we talked about that as well. And a little bit of, we started with the Schrodinger's equation. So today we will be starting with the Schrodinger equation again, covering the basics like a quick recap. Followed by, we will be looking into the quantum gates and quantum circuits. And after that, if time permits, then we will look into the two pending theories of yesterday's session, which was a kind of teleportation and the superdense coding. So this is what our agenda is for today. And yesterday someone were asking question after no cloning theorem as well. Oh, okay, yes, we covered the no cloning theorem as well in details. So one asked a question that how in communication, if you do not copy one state, so how we can actually transfer it if it is not available to the sender as well. So some kind of doubts you had for the quantum communication. So we will try to cover it through the lights of the lights on the teleportation and superdense coding. So this is the basically the background of these two consecutive classes. So in Schrodinger equation, we covered a little bit, like it is a very fundamental equation that governs the principles of quantum mechanics. And basically, in easy words, it is the time evolution of quantum states. Okay. So that entire evolution that can be captured by the Schrodinger equation. Then we have seen two different variants of it, like Schrodinger equation, that was the time dependent Schrodinger equation and the time independent Schrodinger equation. And we introduced a few concepts like a few variables, where we've seen that it's I H cap del del T of psi RT, and that was equals to this Hamiltonian psi RT, where R is the position vector, T is the time, H is the total energy operator or the Hamiltonian operator, or alternatively known as the total energy operator. So why we are into it, suddenly why we actually introduce the Schrodinger equation into picture is because we want to introduce you the idea of the quantum gates and the unitary transformation. So in order to understand that, so which is very fundamental for quantum algorithms and quantum circuit synthesis and all. So in order to understand that we'll have to understand a little bit of the theory behind it or the evolution of that particular concept. So for that, we are exploring the Schrodinger equation. Again, to be very specific, this is a little mathematical as well as theoretical. You might not be initially understanding the direct implication of it in quantum computing, but since our syllabus covers a lot of quantum mechanics for this QT02, so that's why this is a mandate that we have to cover this part. Okay, so this is a background theory. And Hamiltonian operator, this is very important. And then we have seen that Hamiltonian operator is basically a kind of an addition of the both the potential energy, that is the V, as well as the kinetic energy operator, that is T. So the total energy operator is basically the summation of the potential energy and the kinetic energy. And we introduce that this T, the kinetic energy, this is nothing but something like minus h cap square. So this is the reduced Planck constant, which is equals to the h by 2 pi divided by 2m, where m is the mass of the particle times this Laplacian operator square. Okay, and V is of course the potential energy, this one. And then we discussed about the Laplacian operator. This was the partial order, like second order partial derivative of the positions. So this is del square del x square plus del square del y square plus del square del z square. So this gives us a curvature or the spread of a wave function in the Hilbert space. So this basically gives us the curvature or the spread of the wave function. Which wave function? The quantum mechanical wave function. The QM, say quantum mechanical wave function. And if you also remember when we discussed about quantum physics, like everything in quantum physics can be described as a wave function. So this is the same thing that is being propagated through. Okay. So this is still what we covered. And of course, this is in the 3 dimension. You can see it's XYZ. So it's in the 3-dimensional Cartesian plane. Now, now this thing, this thing also gives us another like interpretation. That is, this is also responsible. This is very much responsible for how the momentum affects the quantum system. And you can understand this is the curvature or the spread of the quantum mechanical function. So this altogether gives us an idea or the notion of how momentum, mass into velocity, can affect the quantum mechanical system. So this was one of the postulates that we discussed while we covered the like classical like pitfalls of classical physics and how we entered into the quantum physics. Right? Just to give us the idea of momentum. And this equation governs that particular theory. Now, say T is the motion of particle, the kinetic energy, that is the motion of particle, which in classical, you remember the kinetic energy is p square by 2m. This is the momentum, this is the mass. And in quantum mechanics, the momentum p, classical momentum variable p, is represented by an operator which is minus I h cap, then Laplacian operator. And this comes from the theory, that is from the de Broglie's wave particle duality. We got that lambda, wavelength lambda, is equals to h by p. H is the Planck's constant. P is definitely the momentum. And this is the wavelength of the wave function. Right? So, for a free particle, this can be described as a plane wave. Through the equation psi RT, this is that psi RT that we are referring from the Schrodinger equation, this is the position, this is the time. That is equals to a e to the power I, then k dot r minus omega into t. Where this k is a wave vector and this is equals to a function of this p is equals to h cap k vector. Omega, it is the angular frequency related to the energy operator. And A is the amplitude with respect to the wave function. And T is, of course, as you know, it is the time and R is the position vector. Okay. Now from this, by applying the gradient operator, this to the wave function, how it will look like? Say gradient of psi RT is equals to, if you do that, you will be getting that I k cap psi R into T. And now multiplying both sides by minus I h cap with this particular term, we will get minus I h cap, then psi, I'm not writing the RT anymore, is equals to the h cap, then k vector psi, because I square is minus I square is equals to I square is minus 1, so it's minus into minus 1, that is 1. So this is the thing, and this is equals to p psi. Now since p is equals to this particular thing, that is the h cap k cap, so from these two we can also write that p momentum vector is equals to minus I h cap, then Laplace operator, this thing. Okay, so that was the initial, like what we believed. So here momentum that can be expressed by an operator minus I h cap delta, or the gradient operator, and this is the proof. So this is the definition of momentum in context of quantum mechanics. Now, if we only consider, or if we only focus on the spatial part, what do I mean by that? That is only on the position. So now, focus on the spatial part only. Spatial part means only on the location. That is not time. We do that, then psi r, we will not consider comma t, that thing is equals to a into e to the power I k vector r vector. Now let us interpret it a little details. So delta was your del x, del y, and del z. And this thing, it gives us, or it acts on a scalar field and gives us a vector field. A vector field. right? For example, we will look into that vector field, and it shows how scalar changes in space. Space means vector space. So now if we apply, now so let's apply this gradient operator to psi r equals to a into e I e to the power I k r. So basically we will be applying, this implies that we will be applying each partial order derivative to the exponential function. Exponential means this one. Function. So kr, this means nothing but, this is basically the kxx plus the kyy plus the kzz. How this is true? Because the k vector is nothing but kxi cap plus ky j cap plus kz into k cap, and r vector is nothing but xi cap plus yj cap plus zk cap. Now if you do take a dot product, it will be for the remaining vectors, it will be basically 0, and I it will bring to 1. So that is why k dot r will be kx times x plus ky times y plus kz times z. So we are directly writing this. So psi r, this is now a into e to the power. Now we will replace this entire thing with this thing, and I is there, this small I is there. So it is I into kxx plus kyy plus kzz. So now if we do del psi del x, that is with respect to x. So it will be del x of this entire thing. So what will be the result? This is a partial order derivative with respect to the variable x. So it will be I into kx. This term will come out. Remaining will be treated as a constant times this entire thing. That is a into e to the power I kxx plus kyy plus kzz from differentiation, nothing else, partial order differentiation. So now this entire thing is what? This entire thing is basically your psi r. So this means this is I into kx into psi r. So this is del x of psi, right? So similarly, del y of psi, that will be I into ky psi r, and del z of psi will be I into kz then psi r. Right? So the full gradient, we take the full gradient, that is grad psi r, it is something like I kx psi r, comma I ky psi r, comma I kz psi r. And this is nothing but I. Now kx, ky, kz, that can be written as k vector times psi r. So this is the expression. So this is the expression. Okay. So this was a definition and henceforth is the proof for that. Okay. Now, so this is the proof. Now, from this, we can also infer that grad psi r is ik psi r. This is equals to p vector cap psi r. And this also is equivalent to minus I h cap, that is a reduced Planck constant, grad operator psi is equals to h cap k vector psi r. Okay, so all of them are equivalent because your p vector is minus I h cap delta. Now this is all the derivation or whatever the interpretation from the motion of the particle as we started with the kinetic energy. Now if we enter into the potential energy, say now the potential energy operator, that was V. It is one of the components of the Hamiltonian or the total energy operator. Now this is the multiplication. This operator V is the multiplication of or multiplication by the potential energy operator function VR. So that means this V, mathematically, this means that V into psi R, this is equals to VR psi. Okay. So this is a scalar multiplication. And this particular thing is the potential energy function. And this is the wave function. Right? Now, for free particle, where there is no potential energy, is VR is equals to 0. Okay. That means your Hamiltonian operator, the total energy operator, is only T cap. That is equals to minus H cap H bar square by 2m times grad square. Therefore, the Schrodinger equation for free particle will be something like minus h cap square by 2m delta square, then psi r is equals to E psi r. Okay, where what is E? Here E is the energy eigenvalue of the system. Right? Now this is for the free particle case and how the Schrodinger equation will behave in this scenario. This is say 1. Now the case 2 is case number 2 is a particle in a box. So this scenario This scenario is also known as infinite square wall. So here what we believe is potential energy VR is equals to 0 for 0 less than x less than L, and this VR is infinite for x less than 0 and x greater than L. So this means a particle confined in a box cannot escape, and the potential is 0 within the box. But it is infinite at the walls. So here the Schrodinger looks something like this. So it's minus h cap square by 2m times d square psi x by dx square is equals to e psi x. So this is the solution. So this is after putting all these things and solving the general equation. So I'm not showing everything. You can just remember this one, or you can try it by yourself as well, how you can derive to the general expression. So this is a solution for a wave function. And this is a solution for a wave function and allowed energy levels, and shows the allowed energy levels are quantized. Right? And this is from the psi nx. If you calculate it, psi nx will be the general solution, and your En will be the energy eigenvalue. Why suffix n? You can understand it from the general solution. This is the interpretation. Right? The third one is the harmonic oscillator. So in quantum harmonic oscillator, the potential energy is quadratic in its position. Meaning it is something like this. This is a potential energy. This is half time m into omega square into x square, where m is the mass of the particle, of course. Omega is the angular frequency. X is the position. Therefore, Hamiltonian H, this operator or the total energy operator will look something like this, where this is the kinetic energy part plus this half into m into omega square into x square. This is the the potential energy part. Now, in this situation, for harmonic oscillator, quantum harmonic oscillator, the Schrodinger, if you solve it, the Schrodinger equation will look like something this, that minus h cap square by 2m grad square plus half into m into omega square x square times psi x, that is h psi x is basically E psi h. And if you solve it, it will solution to this will give you Hermite polynomials. You can check it out what it is, but it generally looks like something like the energy eigenvalue general solution will be like n plus half into h cap omega. This is like, this is a very long derivation. We will not go into that part. Okay. So these are the cases. And where this particular thing is used, so its application of all these things, you can see in quantum phase estimation. This is quantum phase estimation or QPE. Now this is very fundamental in Shor's algorithm. This is one of the very important components of Shor's, the QPE. And though primarily Shor relies on QFT or quantum Fourier transformation, but that quantum Fourier transformation, if that is a human body, then a QPE is the brain of that human body, QFT. So QPE is the fundamental essence of QFT, which is again a fundamental essence of Shor's algorithm. So this is used in QPE in extracting the eigenvalues of the Hamiltonian. When if we look into Shor, in maybe not QT02 in later like quantum sessions, then you will be understanding it in details. It's said these are very big theory like QPE, QFT, all these things. So eigenvalues of the Hamiltonian. Okay, so this is one application. Another application is in a decomposition theory in quantum that is called Trotter-Suzuki decomposition. So this is another mathematical decomposition where it is used. So where what is Trotter-Suzuki decomposition is, it is to simulate the Hamiltonian evolution efficiently. What it does is basically it divides the Hamiltonian into smaller parts, so that the part wise, that smaller parts that can be implemented by the quantum gates. So in easy words, this is to simulate the Hamiltonian evolution efficiently by decomposing the H, that is a Hamiltonian operator, into smaller parts such that the parts can be easily implemented by quantum gates. So it's basically a larger Hamiltonian is broken into smaller pieces of Hamiltonian, quantum gates and circuits. So these two are the applications of the like theory that we have seen so far. Now, if we go back, it is all about the what was a Hamiltonian, what was a Schrodinger overall. It was the time evolution or it captures the time evolution of quantum states. Right? That was the earlier theory. So let me take a new page now. So now we are into understanding the simulation or simulating the time evolution of quantum states with Hamiltonian. Right? So we will be analyzing the interpretation of this theory. So in quantum mechanics, the time evolution, and this is the very essence. If you remember, like yesterday we have seen that. So this was the quantum state evolution 1. This is say 2. Likewise, this is say quantum state evolution final. And this is at t equals to time unit 1. So this is the initiator point, and this is the final point. So this is t equals to t final. And we are measuring at how a quantum state through several like stages, intermediate stages, reaches to the final state. So this was your initial state, and this was your final stage or final quantum state. And this entire thing is called time evolution of quantum states, which is governed by Schrodinger equation, and Schrodinger is nothing but the Hamiltonian time evolution. Okay, so in quantum mechanics, the time evolution of a quantum state psi t is governed by Schrodinger equation, Schrodinger equation, which was I h cap del t psi t is equals to h cap psi t, the kth vector. And the solution is psi t is equals to e to the power minus I h cap t by the reduced Planck constant h bar times psi 0. So this was this. Yes. So what is here we are doing is, this is a general solution. You can refer that, understand that. So this was like wave function status at initial, that is time t equals to 0, and this is after all the things are done. So this is the final stage of the wave function status at time t equals to t itself, which is the entire time duration. And we on a quantum computer, we aim to simulate this unitary operator ut is equals to e to the power minus I h cap t by this thing, the Planck's constant. So this is very important. So however, the real Hamiltonians are often the summation of non-commuting operators. Okay, that is, this means this, say h cap is a cap plus b cap, where this a cap b cap, this thing is not equals to 0. And you cannot just say say that e to the power I a cap plus b cap into t is equals to e to the power minus I a cap t into e to the power minus I b cap t. As this is true, as this will be, the above equation will be true only if this A and B are commutative or they commute, say. They do commute. Okay. And here comes the Trotter Suzuki decomposition. Says that if Hamiltonian is H cap is equals to A cap plus B cap, then your e to the power, pardon a little bit here, this would be minus, sorry. So this will be, this thing will be e to the power minus I cap t by n into e to the power minus I v cap t by n whole to the power n. And this is true for large values of n. And this error, or the error in this decomposition of Hamiltonian, decomposition increases or say decreases as n increases. The error will be minimum then. Now we will look into one thing where we will try to analyze the decomposition of the Hamiltonian with respect to a particular operation. So let me take a problem. Say a problem, let us take. Say that is, now we want to see the time evolution. Now we all the theory has been discussed. Now we will look into the directly the mathematical operator with respect to some particular quantum gate. So this is the time evolution of a single qubit in plus state. Plus state. What is plus state? Plus is nothing but the gate 0 plus gate 1. And this happens when we apply Hadamard on gate 0. So this thing is basically your plus. Just after a few minutes, we will enter into Hadamard and how it works and operates. Then we will be having a detailed understanding of it. As of now, just understand plus state is nothing but this thing. 1 by root 2 times gate 0 plus gate 2. Okay. And we will try to analyze the time evolution of this state under the Pauli Z decomposition. As of now, we don't have to also understand what is Pauli Z, but basically this is a phase gate and this is also another single qubit quantum gate. So one quantum state we want to analyze its time evolution with respect to one quantum gate, that is Z gate or Pauli Z gate. Okay, where the initial state was psi 0, that is at time t equals to 0, is equals to plus, which is equals to 1 over root 2, 80 plus k2. And Hamiltonian is H cap is H bar omega by 2 into Z. Z is the Pauli Z matrix. And we now know that any quantum operator is nothing but the outer product form or the Kronecker product form or the direct matrix form, right? So they are ultimately any quantum operator, that means is a nothing but a simple matrix. So this is the Hamiltonian where this matrix Z, which is a Pauli Z operator, is nothing but 1, 0, 0, minus 1. Why and all we will look when we will discuss the quantum gate part. And what is our goal here? Our goal is to find the time evolved state psi t and compute the measurement probabilities in this basis 0 and 1. So this basis or this computational basis. In Shor's algorithm, we will look into that thing that basis also can be of different types. That is, in on what basis we are measuring it. Whether we are measuring it in the 0-1 axis basis, which is called the computational basis, or we are measuring it some other frequency basis, that is called as a Fourier basis. So, which is very essential for Fourier transformation and Shor's algorithm. Just to inform you that bases can in quantum measurement can also differ. But this is our measurement in respect with respect to the 0-1 basis. Let us do that. So step 1. So now we will enter into the solution. These are all the settings that we have. Now step 1 is, now what is gate 0? 1, 0. We know that. What is gate 1? That is 0, 1. So that means my psi 0, which was a plus, is nothing but 1 by root 2 times gate 0, which is 1, 0. And this is 0, 1. So ultimately this is 1 by root 2, 1. Right? Now, step 2 is compute the time evolution operator. Okay. Yeah, just. Yeah. Okay, just let me pause here for a little. Just give me like 2 minutes of time. Okay, I will just come back so we can take some break now. So just we will again start with the solution for this particular time evolution. Okay, just 2 minutes break. Then we will again resume. Okay, okay. So it's 3:55. We will start at 3:58 or something. Yes, pardon me for the interruption. There is another level of Pushpa Raj in my family as well by my two kids. Okay, so definitely. Okay, I'm just looking into a few queries right now. Then I will again go back to the example. Uh, Gradient with respect to what? I hope whoever asks this question right now, it's clear because I have shown you the entire derivation of that. And okay, one asked a question where it is like uniform superposition. Okay, Allah Sakani Kartik. Yeah, hi Kartik. So yesterday's class, yes. So ket 0 minus ket 1 by square root of 2, can it be a uniform superposition? Of course, it is a uniform superposition as well. So similar to ket 0 plus ket 1, there can be like ket 0 minus ket 1 by square root of 2. That is also uniform superposition. Because again, so that is only the difference between the like of the phase. It was ket 0 plus ket 1 or it can be ket 0 minus ket 1, but every time it's a that probability or the like uniformity in the superposition comes with the amplitude part, right? So if that is 1 by root over of 2, so that means the probability is half and half, so that is 50% probable. So that is also an uniform superposition. Yes, another question is by Dr. M. Padmavati. Yes. So, in detail, the correlation between this thing. No, no, no. As of now, just understand that these are concepts which are very like dominantly there in the Shor's algorithm as the quantum phase estimation. So, only what I discussed there is that QPE is one of the subcomponent that is used in Shor's, where we use this kind of like all the Hamiltonian extraction and all whatever we discussed to extract the eigenvalues of the Hamiltonian. So when we will be doing Shor's, we will be or whoever will be doing Shor's, they will be describing you the what is the best like details of the QPE. But since here we talked about Hamiltonian, I just have explained that this is one of the examples. Okay, or whenever you solve it or see here we're giving you the general solutions, right, for both the wave function as well as the energy eigenvalue. So while we are doing that finding the general solution for the energy eigenvalue, this particular process you can see a replication of this one in your when we do the QPE in short, where we estimate the phase in terms of the eigenvalue itself. That was the first application, and second application was the Trotter-Suzuki decomposition, which has no correlation with the Shor's algorithm. It's a separate one. All right. So this basically is by like the process of breaking a larger Hamiltonian into smaller components. Okay. So I think these are a few doubts. Now let me just go back. And for QPE, understanding QPE, you have to wait for the till the Shor's algorithm. It is very big, like it's itself a 2 hour session. The QPE. Okay. Okay. Now let me go back. I hope your doubts are clear. Now we will again talk about the doubts at the end or somewhere in the middle. So, yes. So, what we were doing, we were about to find the time evolution or time evolved states psi t, where we are started with psi 0. And this was our psi 0, which was a plus state. So this was the actually the state 1 by root 2, 1 and 1. And this is for the 0th position and this is for the 1th position. Let me mark it like that. So this is basically 1 by root 2 ket 0 plus ket 1. Okay. Now, second step was to compute the time evolution operator. That is the this operator, unitary operator ut, which was equals to minus. This is the general definition. Now we will try to understand that for our specific application, how to compute this operator. So let me plug in. So if I just plug in the definition into the application, so H cap is basically the Planck's constant. This is the reduced one. So reduced Planck constant omega by 2 into Z. We have seen that. Therefore, our ut will be, if I just put it over here, so it is minus I H cap omega by 2 into z, z into T by H bar. See the definition? So of course H cap will be cancelled, and it will be something like minus I omega T by 2 into Z. Now, I have told also, like in yesterday's class, that every quantum operator is nothing but a quantum matrix, and all the quantum matrices are nothing but a self-adjoint matrix or an Hermitian matrix. Now, for a Hermitian matrix, for a Hermitian matrix, those who joined first today, like this is your starting first class for QT02, please refer all the initial 3 days lecture entirely. Then only will be able to understand it. Though I'm trying to do the recap as max as possible, but all the minute details, the mathematical details, I'm unable to do that. So for that, you have to actually go back to the all the previous 3 lectures. So please follow them. So for a Hermitian matrix, like Pauli Z, which we also mark as Pauli Z, like sigma Z, then Z square will become I. What is the proof? Say Z is 100 minus 1. So let me compute Z square. 100 minus 1 into 100 minus 1. So what is the multiplication? 1 into 1 plus 0 into 0, that is 1. 1 into 0 plus 0 into this, that is 0. 0 into 1 plus something into some 0, that is 0. 0 into 0 plus minus 1 into minus 1, this is minus minus plus, so this is 1, and this is the identity matrix. Proved. Now, therefore, e to the power minus I theta z is what? Now, this is from Euler's theorem. You should know what is Euler's theorem. That is e to the power I theta is nothing but cos theta plus I sine theta. It's a very well known and very famous Euler's theorem. Now here it is minus I theta into z. So this will be from the similar expansion, it will be cos theta minus I sine theta times z. Okay. Now if nothing is there, then I can write it as an identity I. This is the same thing. I can multiply that. So this is cos theta into I minus I sine theta into z. Now remember this equation. So for theta equals to omega t by 2, we have what? We have, what was our ut? Our ut was, our ut will be cos omega t by 2 times I minus I sine omega t by 2 into z, only by replacing theta with omega t by 2, nothing else. Where of course I is 1001 and z is 100 minus 1. Therefore, ut can also be written as, from this equation, you can understand that this can be written as cos omega t by 2, this entire thing, okay? Cos omega t by 2 minus I sine omega t by 2. This is 0, this is 0, and this is cos omega t. How I am getting it? Just by multiplying it, right? With the 1001 likewise. And this is 100 minus 1. So cancelling out everything and after applying the multiplication, then the subtraction, we'll get this thing. So this is plus I sine omega t by 2. Yes. So this is the thing. Now again, this is nothing but from the Euler. This is what? Cos theta minus I sin theta. Right? So this is nothing but e to the power minus I omega t by 2. Why? Just to make up this minus sign. E to the power minus I theta is cos theta minus I sin theta, where theta is basically omega t by 2. So this is e to the power minus I omega t by 2. This is 0. Sorry, this is 0 and this is e to the power I omega t by 2. And this is what finally I got, that my operator ut, which I am going to apply, that is nothing but e to the power I omega t by 2, 0, 0, e to the power plus I omega t by 2. So this is the end of step 2. Now, step 3 will be, now we will be applying the ut that we got at step 2 on the initial state. What was the initial state? Psi 0. Get vector. So if I do that, that means my psi t, there is a final quantum state, time evolved quantum state psi t will be nothing but this ut when it is applied on initial state psi 0. This is the thing. So that means ut is what? E to the power minus I omega t by 2, 0, 0, e to the power I omega t by 2. And what was my psi 0? This was 1 over root 2 times 1 and 1. If you multiply this, can you do that first of all? Of course you can do that. This is 2 cross 2, this is 2 cross 1. So the result will be a 2 cross 1 matrix. And if you multiply it, so it will be e to the power minus I omega t by 2. And this is e to the power I omega t by 2. And from this thing, we can write it that psi t is nothing but 1 over root 2, because this is for the 0th one and this is for the 1th. So that means this is the amplitudes itself. So e to the power minus I omega t by 2 get 0 plus e to the power I omega t by 2 get 1, because these are nothing but the probabilistic amplitudes or the expansion coefficients. Because initially when it was 1 and 1, we used to represent this part as 1 by root 2 get 0 plus get 1. So right now, instead of 1, there is e to the power minus I omega t by 2. So it is e to the power minus I omega t by 2 times get 0 plus e to the power I omega t by 2 times get 1. Clear? So this is the final step. Now what we also are left with, what about our task? It is also, so the time evolved state psi t we have computed. Now our objective is to compute the measurement probabilities in 0-1 computational basis. Right? Now in order to do that, we have to do the step 4. So it is basically to describe the measurement probabilities. So in order to do that, we will be applying the inner product of psi t and 0 in the order 0 and psi t, because we want to now measure what is the probabilistic amplitude and probability of having state 0. So that is why here we have taken state 0. So this is nothing but this thing. By now, you should be confident about this notation. This is the tensor product. And this is bracket 0, which is 1, 0 in the row vector form. And products of this thing, which is 1 by root 2 e to the power I omega, sorry, e to the power minus I omega t by 2 and e to the power I omega t by 2. So this is 1 by root 2. Then the product will be 1 into e to the power minus I omega t by 2 plus 0 into e to the power I omega t by 2. So this will be cancelled out, of course. So you are left with 1 by root 2 e to the power minus I omega t by 2. Then your probability of 0 will be this expectation square. So this is 1 by root 2 e to the power minus I omega t by 2, that mod square. Now if we apply the identity, so applying or using the identity e to the power I theta, this is equals to 1. For obvious reasons, as cos square theta plus I square theta, sorry, sine square theta is equals to 1, and e to the power I theta is nothing but cos theta plus I sine theta. And this one is nothing but root over of cos square theta plus sine square theta. So from all these like theory, we know that e to the power I theta mod value is equals to 1. Right? Therefore, our PR0 was this. So the probability of state 0 will be 1 by root 2 square into e to the power minus I omega t by 2, that square. Now whatever be here, that will be 1. So this is 1 by root 2 whole square, which is equals to half. Okay. And probability of 1 will be just exactly like the same thing, e to the power I omega t by 2 whole square, that is 1 by root 2 whole square into 1, that is half. And this proves the probability. Okay, so this is what we were supposed to cover, and this gives us an essence of all the mathematics behind the Hamiltonian equations and all. So anyone has any question till this part? There are like very obvious reasons that you might be having questions, but what my suggestion is that you should actually be doing a lot of recap of like today's class, at least all the mathematics part, because in I mostly do not skip any of the like deductions, but if maybe I have done some jump, the intermediate lines are not written, so for the best understanding you have to just take a pen and paper and have to do that all the calculations by yourself. And wherever you are having any doubt, you can actually refer further theories for that on internet. That will actually give you the full essence. Okay. So any doubt till this part, or are we good enough to go to the quantum gates and quantum circuits? Only after that, once we at least done a basic of the quantum gate and quantum circuit, we can cover the teleportation. Is there any doubt, or is it all good? Please let me know. Okay. Step 2. I will repeat step 2. Other than that, there is no doubt. I and Z implementation. Cos theta into I, just so that I can write it in that matrix form. Because Z was in matrix form. Definitely, definitely that is the best understanding, that you have to go out not only once, at least maybe 3 to 4 or 5 times for the initial first understanding to be like clear. They're very complicated concepts. Yes. So, okay, I got a few questions. There is a doubt in step number 2. Let me go back. And also, like, why I have introduced the I with cos theta. Where is it? The step number 2. Yes. So this was the general expression given to us. Z was that matrix 1, 0, 0, minus 1, which was the Pauli Z operator. Okay. Now ut was also defined as ut is equals to e to the power. These are by definition. This is by definition. What I'm doing is I'm just replacing this in this particular Hamiltonian, like this expression into this Hamiltonian H cap. And I'm getting this. Now several things are cancelled out and we are left with ut is equals to this thing. Okay. Now after this, just jump to this particular place where only one observation I have shared here, that is this thing. Okay, that is e to the power minus I theta z. That can be written as, if I theta is equals to cos theta plus I sin theta, then I theta z can be written as cos theta z plus I sin theta z, something like that. So from that I have got that this is cos theta into I, and this is I sin theta into z, where I sin theta z comes for the obvious reasons. And here it is basically, since I want to represent it in the matrix form, just like this, I want to represent it in the matrix form. I have introduced an identity matrix because anyway it will not be having any effect on this thing. Okay, so this is Z, and there I have just shared that ut, after you have done all this multiplication, it will be cos omega t by 2, all these things after you have done that. So this will be cos omega t by 2, 0, 0, cos omega t by 2. That's this product. And this will be I sin omega t by 2 times like 1, 0, 0, minus 1. Accordingly, it will be. So after you do all these things and you multiply with I and all, you will be getting this particular thing. So now again from Euler, if I just go back, so this is nothing but this thing. And this is nothing but this particular thing. They are equal. Again from the Euler theorem. So how we are getting it? Using the Euler's theorem. Here also. And the rest is what we have got. Okay. I hope it is clear. Now we will enter into the quantum gate part. Let me just show it here. This part is very, very, very essential for quantum computing. Very essential. You can say that for computing, it is a fundamental building block. Without this, you cannot proceed. And these are just the information that you should be knowing first. Then it is the application of this information. Okay. So first of all, what are quantum gates? How do they look like? What is their matrix format? We will look into all these things. So quantum gates basically are of, you can say broadly, very broadly, two types. That is a single qubit and multi-qubit. But why the third type I have taken here is because there are also, just like single qubit, inbuilt some 2-qubit quantum gates as well, which are very much in use. So instead of only greater equals to 1 and putting it in multi-qubit gates, I'm just keeping a separate category called a 2-qubit quantum gates. And multi-qubit, for some reason, I have kept them separately. Single qubit gates are mostly, the most important gates are, which you should be knowing, is Hadamard, then it is your sigma x, sigma y, and sigma z. These are all, okay, this is the Hadamard matrix. These are called Pauli, sorry, Pauli matrices. These are also known as X, capital Y, capital Z. Both are having the same meaning, right? Primarily, and there is also another one very general gate, which is say R theta. This is a rotation gate. And there are, in this rotation, there are several types of it, like S, T, and something like that. And how do they differ? They differ just by the angle, by theta, or the angles only. Like specifically, some of the gates are like hardwired, like pi by 4, pi by 2, and like this. Okay. Now, 2 qubit gates are very, very important as well. Primarily, the C naught gate, which is a controlled knot. Then comes the like C phase gate, which is a controlled phase. Then comes the swap gate. Okay, mostly these are the ones. Multi-qubit gates are anything which is more than the number of qubits greater than 2, and they are mostly the most important ones are Toffoli gate and Fredkin gate. So Toffoli is alternatively what is like controlled or C-square NOT gate. Controlled NOT gate. Fredkin is also like something like controlled swap. And of course, there can be any generic gate, any generically or say generic uh, designed gate with n greater than 2 will also belong to the multi-qubit category. Okay. Now, what are the gates that directly you can make use of? Out of these things, like all these gates you can directly use. And also, like Toffoli is the one gate that you can directly implement, and the Fredkin. Okay. In Qiskit, you can use it. Now, out of these, what are the most important gates? All these things are there. What is the most important? Where you will be like watching the maximum application? That is Hadamard, Pauli X, Pauli Z. Why not Pauli Y? I will just mention that because of the difference in the measurement basis. So these are all with respect to several bases. Pauli Y is in complex plane where we generally do not measure anything. Okay. Another one very important one is the C naught gate. Then it is very, very important. Then it is a C phase gate and the Toffoli gate. These are the primary gates which has the maximum application in any of the quantum algorithms. Okay. Now, so we will first today doing all the basic gates. Say Hadamard gate. Where it is used for the purpose of bringing superposition. How does it look like? It looks like this in a quantum circuit. How to write the code for it? Like H of say Q0. What does it mean? That you have to apply Hadamard gate on qubit whose name is Q0. What do I mean by HQ0, HQ1, HQ2. This means there are 3 qubits, and all these 3 qubits you are applying Hadamard. So this is the exact look in the quantum circuit that is in the physical actual implementation. And often schematically for multiple Hadamard gates together, we often write it like this. Basically this, like writing this and this, they are equivalent. Okay. Now if another very important point is how the Hadamard matrix looks like. Hadamard is what? Hadamard gate is an operator. So Hadamard gate is an operator. Any operator is an Hermitian matrix. So ultimately Hadamard gate is nothing but some matrix. Mostly square matrix kind of thing. Or square matrix, or at least one of the matrix component will be in the 2 to the power, in a power of 2. Right? So Hadamard matrix looks like this. This is a 2 cross 2 Hadamard matrix. So this is a single component of a like fundamental unit of the Hadamard matrix. Clear? Now if we want to expand it, say I want to apply a 4 cross 4 Hadamard matrix. And how it will look like? It looks like this. So 1 by root 2, 1 by root 2, 1 by root 2, and minus 1 by root 2. This is the fundamental one, right? This one. So let me put all of them together. Okay. And similarly, there will be 4 quadrant kind of thing. In second quadrant also, it will be exactly same. In third quadrant also, it is exactly same. But in fourth quadrant, it is exactly the inverse, or say negation, or you can say. So it will be minus 1 by root 2, minus 1 by root 2, minus 1 by root 2, and 1 by 2. And all these Hadamard matrix, they are part of the Walsh-Hadamard transformation. There is one theory in networking where you have seen actually this Hadamard matrix. But maybe you're not remembering because it's written in terms of 1, 1, 1, 1, not in form of the 1 by root 2. Okay. You know what it is? It is called the CDMA, code division multiple access. You can do a double check there. So there also we apply the Walsh-Hadamard transformation in order to get a particular code. That is the essence of the CDMA technique. Remember the story where a Chinese, a Japanese, a maybe Indian, a British, all these men are together sitting in a room, and there are pairs of it, like 2 British, 2 Indian, say 2 Indian are communicating in Hindi, for example, or in say Telugu or in some other language. 2 Chinese people, they are talking in Chinese. Two like people from Spain, they are talking in Spanish. Likewise, but though they are all communicating together, but because of that specific code, because Chinese people will not be understanding Hindi, Spanish, or other language, they only will be able to interpret Chinese. Similarly, for the Indian as well, they will only be able to interpret Hindi, not any other language. So, though all will be sharing the same space or the same channel, but even after that, there will be no conflict, right? So that was a theory. So there you can see the same thing. So all these are separate codes which are used to give the access for a multiple host to communicate together. Anyway, so similarly, a 8 cross 8 matrix, Hadamard matrix will look like. Let me just write it down. So it's a 1 by root 2, 1 by root 2, 1 by root 2, 1 minus 1 by root 2. Now the fourth part will be taken as it is, 1 by root 2. this thing. Now this entire thing will be copied here. Same thing will be copied here. So it's the same. It's the same. And the negation part will be copied here. Everything will be negated. So it will be something like this. And then this will be positive. Yes. So likewise, you can have an expansion. When this particular 8 cross 8 is used, if you have to apply it on a, say, quantum state, which is a pure state, say ket 000, which is 1000000, which is for the 008th position. Then we need a 8 cross 8 Hadamard matrix in order to apply on a 8 cross 1 column vector. Okay. Now that we are done with the Hadamard, another very important thing is, what is the application of Hadamard on ket 0 and application of Hadamard on ket 1. So if you apply an Hadamard and this is ket 0, so what it will be? Hadamard on ket 0. This is what we want to do. Hadamard is basically 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. And ket 0 is nothing but 1, 0. So if you simply multiply them, it will be 1 by root 2 into 1 plus 1 by root 2 into 0, that is 1 by root 2. And here also 1 by root 2 into 1 minus 1 by root 2 into 0, that is 1 by root 2. So this is 1 by root 2 taking as common 1, 1. Now this is a familiar kind of thing for you. So this is ket 0 plus ket 1. And this entire thing is also referred as only plus, which we were talking about. Okay. Now similarly, if we apply, say, the initial state, how to get the initial state at 1, I will discuss later. But say 1 is fed to an Hadamard gate. So H on 1 will be like 1 by root 2, 1 by root 2, 1 by root over of 2 and minus 1 by root 2 times. Now ket 1 is nothing but 0 and 1. If you multiply it, so it will be 1 by root 2 into 0 plus this one, that is 1 by root 2, and 1 by root 2 into 0, that is 0, plus minus 1 by root 2 into 1, that is minus 1 by root 2. If you take 1 by root 2 as common, it will be 1 minus 1. So this is nothing but, this is for the 0th position, this is for the 1th position. So this is 1 by root 2 times 1 into ket 0 plus minus 1 into ket 2. Right? That is how we write. That is like these are the simply the coefficients. So this is 1 by root 2 times ket 0 minus ket 1. And this thing is nothing but ket minus. Okay. So Hadamard actually brings this superposition. Another example is if I have, say, 2 qubits, a 2 qubit Hadamard basically, which is a 4 cross 4. Let me write it down. Say I'm applying this on what? On basically ket 0, 0. So 2 qubit Hadamard is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Then this thing. And this is ket 0, 0 is nothing but 1, 0, 0, 0. Let me just do the multiplication, show something to you. So this is one, this is only, all the remaining variables will be 0. So this is 1 by root 2 into 1. All the variables are 0. And similarly, this is 1 by root 2 into 1, and all of them are 0. And this is 1 by root 2 into basically 1, and all these things are 0. Yeah. Similarly for here. So this means this is nothing but, just take it outside. So this is 1, 1, 1. Pardon me for one thing, that is whenever this is a 4 cross 4, basically because of the 2 qubit hadamard means a 2 hadamard. So basically it is like it will be half. So I'm not replacing it fully, but it will be half. Because there are 2 hadamard, so it's basically like this. Minus 1. Product of 1, 1, 1 minus 1. Okay. Oh, sorry. Here also there is half. So ultimately this means this will be another 1 by root 2. So this is 1 by root into 1 by root 2. So that is half into 1, 1, 1, 1. Which means half into your kit 0, 0 plus kit 0, 1 plus kit 1, 0 plus kit 1, 1. So this is a superposition. And only if the initial state is 0, 0, you will be getting it all plus, like 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. If you take another state, say you are doing it on 1, 0, so it will be like 0, 0, 1, 0. If you do it on that, definitely the values here, it also will be a superposition, but the values or the phases that will be different. Okay. So this is all about hadamard. Now, let me take that gate, that is the X gate or the sigma X gate. What it is? It is simply the NOT gate or the inverter. Meaning if you give 0, it will, like X will make it 1. If you give 1, then X gate will make it 0. How it looks like? The matrix form. The matrix form is 0, 1, 1, 0. Let me check a quick check X on 0. So that means 0, 1, 0, 1, 0, product 1, 0, which is the gate 0. So this is 0 into 1 plus 1 into 0. That is simply 0. This is 1 into 1 plus 0 into 0. That is 1. So X on gate 0 will make it gate 1. Similarly, X on gate 1 will be 0 into 0 plus 1 into 1. That is 1. And here it is 0. That is gate 0. So this is the inverter. Now how it looks like in a matrix? Simple X. Nothing more to talk about it. Done. Next is the Z gate. The Pauli Z gate. Now this one actually flipper. This flips the value. If it is 0, it make it 1. If it is 1, it make it 0. But Z gate is the phase changer. So this changes the phase unconditionally. Meaning if you have 0, then Z will do nothing, because 0 phase plus 0 minus 0 doesn't make any sense. So it will be 0. But if it is 1, then Z gate will make it minus 1. Now is the like theory that how Z looks like. So it's basically 1, 0, 0, minus 1. A quick proof. What happens when we apply Z on 0? So if we apply Z on gate 0, that means 1, 0, 0 minus 1 is applied on 1, 0. So it will be 1 into 1. 0 into 0 is this one. This is 0. So gate 0 has no change if it is applied through or if it goes through a Z gate. But if it is 1, then it is 1 0 0 minus 1 times 0 1. And that is 1 into 0 plus 0 into 1, that is 0. And this is 0 into 0 plus minus 1 into 1, that is minus 1. So you can take minus as common. So this is minus, right? Now the third one that I want to talk about, or not the third, the fourth one, is the general rotation gate. So general rotation gate is basically something like 1 0 0 e to the power I theta. Okay. Now if you notice, say if my theta is pi, then what will happen? The gate will be 1 0 0 e to the power I pi. What is the value of e to the power I pi? This is nothing but cos pi plus I sin pi. This is 0, but this is minus 1. So this will then become 1 0 0 minus 1, and this was the z gate. Right? Similarly, if you put theta equals to pi by 2, you will be getting another gate. If you put theta equal to pi by 4, you will be getting another gate. But if you put a generic theta, then this is the generic rotation gate. Similarly, they are called, I guess, I don't remember exactly like ST and all. They are just the like changing the angle, nothing else. Okay? Clear till this part? Then the next one, is 4 we discussed. The C naught, which is the control node. Again, do a lot of focus here. Control node gate. What it is? It is a 2-qubit gate, first of all. Meaning it has two inputs. 2-qubit, two input. What are they? Control and target. So its truth table looks something like this. Say control, target. And these are input. As well as on the same variable, what will be their effect? So this is output. So combinations can be 0 0 0 1 1 0 and 1 1. Always true. This is a combination. So remember, if control is 0, first of all, control is such variable which remains unchanged during the input as well as the output. There is no effect on control. So control will be always this thing, irrespective of input and output. But target will flip by the effect of control only when control is 1. What I said? Target will be flipped on effect of control if and only if control is equals to 1. So flip. So here control is 0, so there is no change in target. But here control is 1, so it will make this thing as 1. And here control is 1, so it will flip your target from 1 to 0. Right? And how it looks like in the quantum circuit? So there are two definite two inputs. One is control, another one is target. Right? The field circle is control, and this one, the ZOR kind of symbol, this is the target. And this Hadamard followed by C naught, this combination brings the very essence of entanglement. And where it is used, entanglement? In communication. we will look into. Okay. Okay, I have 5 more minutes, then I will take the query. Let me just cover a little bit of the remaining gates. So C not we covered. Next is the, okay, so we covered header mode, phase gate, not gate, then the general one and the C not. Next is the control phase gate. It's also two input. So it looks like this. These are the two input. This is control, this is target. So this is your simple Z gate or phase gate. Okay, and this is a control variable. So this says only change the phase of target, that is 0 will be 0 and 1 will be -1 if and only if control is equals to 1, right? So that means control target, these two are the inputs, and if control target are output as well, then 0 0 0 1 1 0 1 1 are the four configurations. Then when control is, first of all, there is no effect of control. When control is 0, there is no effect of on target. But when control is 1, if target is 0, then apply a Z gate on target. So that will make no change. It will be 0 only, but only here on application of Z, it will be -1. And this is how it looks like in a Qiskit or a quantum circuit, right? Then the next one is the swap gate. Swap gate is pretty simple. Whatever be your input, just make it, if 0 is there, make it 1. If 1 is there, then make it 0. And this is something, this looks something like this in the Qiskit circuit. This means a simple swap. You have something here, so qubit 0 and qubit 1. So this means a swap function will be applied on Q0 qubit. Nothing much. Next, very important one is the Toffoli, which is also known as C-square NOT gate. So this is a 3-input gate. And here you have 2 controls and 1 target. So the logic is only flip the target when both the controls are 1. So say C1, C2 and T. These are the 3 inputs. And C1, C2, T are the ones at the output level as well. So it's 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1. So whenever the all the, like in all the first 6 cases, there will be no change, right? Because both the controls are never 1. Both has to be 1. Both C1 and C2. So that means there will be no change here. But here, since in both the cases, both the controls are 1, so 0 will now become 1 and 1 will now become 0. Okay. And in a quantum circuit, how it looks like, so it looks like this. The C-square naught looks something like this. where this is control line 1, this is control line 2, this is the target. Okay. So I want to pause here and also, okay, how in Qiskit it looks like CC naught, Q0, Q1, Q2. So from this you have to understand that Q0 and Q1, whatever you have put first, Q0 and Q1, that is your control variable, and Q2 is your target variable. Similarly, just check with the Fredkin, it is also the controlled swap gate. So you will swap based on the control input. So of course, if there is one input for the control, and depending on that, whenever it is one, you will be swapping the contents. Okay, it's 4:56. We covered the basic ones, so that we have at least now a little bit of understanding of the base. Please do a recap of these things. These are very essential. C naught and CC naught primarily, but you should be having a very good understanding of this thing. So tomorrow we will start with teleportation. Before that, we will start with the Bell state or entanglement first. Once we have our understanding of the Bell states or the Bell pair or maximally entangled pair, then we'll go to the jump to the that teleportation. Want to pause here. So if you have questions, you can ask. Let me stop sharing. Phase has no effect of on 0 because plus 0 and minus 0 will not make any sense. This is not flipping. Okay, not infinite potential, rather it's we are just assuming that it's somehow like a maybe it's potential, it cannot do anything within the box, so at the walls of the box it has an infinite potential energy that it has energy conservation on all those things, right? These are all assumptions of the several cases, like ideal cases. Okay. And phase has no effect on 0 mathematically also. You have seen like phase gate is 100 minus 1. Whenever it is applied on qubit 0, that is on 10, it will exactly be 10 itself. That means Z on application, like application of Z on 0 keeps it 0 only. Note it. Yes, yes. Hadamard 1. Yes, I just mentioned that will be like 1 by root 2 into 1 by root 2, so that the coefficient will be half and the probability is 1 by 4. Exactly true. Yes, yes, yes. Please correct. I just have taken one like Hadamard coefficient, that is 1 by root 2, but another coefficient will also come. Whenever we are incorporating or integrating two Hadamards, it will be 1 by root 2 into 1 by root 2, that is 1 by half. So that is the coefficient, therefore the probability will be 1 by 4. Okay, I think I just, whatever, if you have some doubt, we can discuss, yes, tomorrow. Mm, uh, I have to actually leave today. I think please just hold on your question or write it down. Tomorrow we will be having that discussion.
Yeah. Okay, ma'am. I think I understand that you are in rush today. Thank you,
Yes.
ma'am. for the nice lecture. Actually, today's lecture is very, very important for the rest of the courses, even other courses also. So thank you once again. And I think more or less most of the questions are already been dealt. And as ma'am already explained, kindly post these questions tomorrow. I think we can take in the beginning of the tomorrow's session.
Yes, definitely, definitely.
Right, right, right. So,
I have to leave. Thank you, sir.
okay. Thank you, ma'am. Thank you very much.
Thank you, everyone.
So dear students, dear candidates, we'll again meet here tomorrow at 3 o'clock and we'll continue with the fifth lecture of Nivedita ma'am. And as if your question towards the end has not been dealt today, what you will do is in the beginning of tomorrow's session, we'll take up those questions. Please keep the questions with you tomorrow as we start the session with ma'am. Kindly pose the questions once again. I will just again remind you once again at the beginning of the session, and we'll take the questions one by one, right? And ma'am will, as ma'am already said, ma'am will deal with those things. So thank you, everyone. And also already the lectures up to all the PPTs up to lecture 3 has already been posted in Canvas. So please visit over there. One more important thing is probably by tomorrow we'll let you know the schedule of those quiz that Willis had already explained to you, and probably end of this week we'll try to have the first quiz. So again, once again, thank you, and let's meet once again tomorrow at 3 p.m. Right? Yeah.